Now, if we talk about mixture distribution, mixture model, we have this thing here. So we have a parametric classification with normal distribution. We assume that we have one group per class. So with several modes in a single class, so we have one class, but we have many modes. Just get back to the example that I gave you before. So we say that we have different ways of writing a A. So we can write this as a capital A, small letters A, and more typographic book style A. So these three different ways are different modes, and we should not kind of mix them together because it will not be well approximated by some kind of normal distribution just looking at the shapes. And we don't do this with images, but it's kind of an example to visualize this thing. So the point is to make use of what we call a mixture distribution, a mixture model. So we are combining several density functions to describe something with several groups. And as such, it gave us like a distribution. So this is the distribution over x's, which is in fact combining k groups. So we have groups from 1 to k. And we have here the density function for group GI. So GI is group I. And this is the function describing how values are distributed in that group times the prior of GI. So it's basically how much do we get from samples from GI in the whole set or in the whole distribution. So this thing is interesting, but for using it, we need to know in advance what are the different groups. And if we don't know, if we are not able to see, oh, this is from first group, this is from second group, it gets much harder. So if we are able to say, oh yeah, this is a data from group 1, this is a data from group 2. So we have these two groups that are modeled as normal distributions, and then are joined together as a mixture distribution. This is fine. If we don't have this information to group them, we need to make use of some kind of unsupervised learning approach, clustering basically, to learn these groups. And this is much complicated, and we will see that later at the end of the semester. So if we're looking at more specifically at multivariate normal distribution, so mixture distributions for components based on multivariate normal distribution, we've got the component density, which is described. So for one component, we have directly a normal distribution. And the parameters of that mixture distribution is basically the prior mean vector covariance matrix from group 1 to group K. And all packed together, so these three elements, this parameterization of one component is put together with the parameterization of the other components. So we have key components, plugging it up together, we have the complete parameterization of our mixture distribution. So then we can get, we have the density function P, the likelihood of X coming from that mixture distribution described by this here. We are looking possibly at the proportion in the group GI of the mixture. So basically the proportion is the prior, is basically what is the probability of getting a sample from group I in our mixture distribution. And the sum of these probabilities should be equal to 1. So if we have 3 groups, we should be sure that the probability of G1 plus P of G2 plus P of G3, summing these 3 is equal to 1. Otherwise, there's something missing. We are not really using probabilities. And then we are able also to evaluate the probability that a given X belongs to a group. You know how to do this? Looking at this equation, you should be able to figure this out. This is based on the Bayes rule. So using the Bayes rule here, we are able to compute the posterior probability, which is stating that what is the probability that data instance X is coming from group GI. And all of this is basically the same that with classification using the Bayes rule, except that we are not looking at classes, we are looking at groups. So groups is different in the sense that they are building up components from a mixture distribution.